numericals. Some more important numericals are there from the sequence components. Okay, so next numerical is a balanced star connected load. A balanced star connected load takes 45 amps from a balanced three-phase 4-wire supply. If the fuse in the two of the lines are removed, find the symmetrical components of the line current before and after the fuse are removed. So we have to find the symmetrical components before and after the fuse. So this is the three-phase system which we'll be having, and fuse is present everywhere in or the three lines. Let us say we have these lines as, and this is R, and this line is Y, and this is B. So we have these lines like, and this is a neutral point shown here. Now before, we were talking about when we are not removing the fuse. Before the fuse is removed, let's see. Okay, so before fuse is removed or fuse removal, before fuse removal, we'll see now. Before fuse removal, we can see this before that, before finding the symmetrical components, what is given to us is that it's very clear that star connected load takes 45 amps from a balanced three-phase supply. So if two of the lines are removed, then it's after removing the fuse. So given first will be, it's a balance conditions we have to assume. It will be IR will be 40 at an angle of 0 degree. Similarly, IB will be 40 at an angle of 120 degree, and sorry, minus 120, and then RY, this is Y here, sorry. Okay, so this is Y, and RY and B phase sequence is like this. This 40 at an angle of plus 120 or minus 240, it is one and the same thing. So this condition is before fuse removal. The system was balanced. Let's remove this. Let me copy this. Okay, it's a copy and we can paste it here. Okay. Okay, this is this which is given. This is before the removal of the fuse. Before the fuse removal. So this condition exists when the fuse is not removed. So this condition is going to exist. Okay. Now we have to find the symmetrical components. This is the value of the current. These currents are right now, these are balanced currents. There's no problem in this case. So, but we have to find the symmetrical component before the fuse is removed and after the fuse is removed. If the fuse in two of the lines are removed, so before that and after that we have to find. So before fuse removal, what will be the symmetrical components? IR0 will be equal to 1 by 3 IR plus IY plus IB. So if you add them together, this will come out to be 0. Similarly, then positive secants will be written as 1 by 3 1 by R plus A Iy plus A square IB. So if you consider this, again you will get 135. I'm not substituting the value. Divide by 3 at an angle of 0. So you are going to get 45 at an angle of 0 amps in this case. And last is negative secants component, that's IR2. So it will be 1 by 3 IR plus A square IY plus A AIB. So if you calculate this also, this will also become 0 amps. So these values are, if you have to substitute the values, just these values. And this is a condition before the fuse has been removed, before the removal of the fuse, these conditions. Before the condition, this fuse has been removed. Now, after the fuse has been removed, let us copy this. So let me copy it. Let me copy this. Copy and let me paste it here. Okay, so this is when this will say after fuse removal. What will happen? After the fuse removal. Okay, after the fuse removal, what's going to happen? We can see in two of the lines we have removed the fuse. So we'll remove the fuse from two of the lines. Here, so let's say we have removed here. So we will put it like this. We will remove the fuse like this. Okay. So this is fuse here. Okay. So we have removed like fuse this. So what will be the symmetrical components? Now, first of all, we'll write the values of the currents. In first case, current will be same, 45 at an angle of 0 amps. Now, second, because we have removed the fuse, so both the currents will be 0. Fuse is a small wire which is connected, and in case of any abnormality, it will protect the equipments because that wire will melt down, and then it will protect the other equipments which will be following it. So we are removing completely this, so the current will not be able to flow this unless we reconnect it and repair it. But the symmetrical components will be then what? Symmetrical components, first is the zero sequence component. Zero sequence component will be 1 by 3 IR plus IY plus IB, and this will be 45 at an angle of 0 degree divided by 3, and this will come out to be 15 at an angle of 0. So IR1 will be IR plus AIY, A square IB, Y and B are 0. So again, this will be the same thing. 45 at an angle of 0, divide by 3, and that will be 15 at an angle of 0 amps. Third, IR2 will be IR A square IY plus AIB. That will be again 45 at an angle of 0, divide by 3, and that will be 15 at an angle of 0. So this is what we have in place. These are the symmetrical components. But if he has asked to find I by 1, we can find all the symmetrical components. This time So that is A square IR1. We have already seen that one. ABC, and this RYB. AB is Y. AB1 will be equal to, ठीक है, A square I A1. So this is 1 at an angle of 240 degree multiplied by 15 at an angle of 0. So that will be 15 at an angle of 240 degrees. So similarly, IY2 we can also find. IY2 is AIR2, because you can have everything in terms of IR. So 1 at an angle of 120 into 15 at an angle of 0. So we can see this is 15 at an angle of 240 degree amps. So similarly, we can find IB. IB1 is AIR1, and that is 1 at an angle of 120 degree multiplied by 15 at an angle of 0, and that will be 15 at an angle of 120. Sorry, here it should be 120. How come it's 240? Okay, it shows 120 degree. So 120 degree. Okay. So IB2 will be A square IR2. That will be 1 at an angle of 240 degrees multiplied by 15 at an angle of 0, and that will be 15 at an angle of 240 degrees. If you want to cross check, you can see the symmetrical, unsymmetrical currents. IY will be IY0 plus IY1 plus IY, sorry, negative sequence will be IY2, and this is 0. This you can calculate, it will become 0. IB will be IB0 plus IB1 plus IB2, and this also will be 0 because fuse has been removed. So this is what we had to find in case of first numerical. Fuse has been removed, and fuse, before the removal of fuse and after removal of fuse, it should be very clear that what we are going to do. Now next question is a delta connected. Let me draw that diagram for you, delta connection. Okay, so we have a delta connection like this. We have a delta connection like this. And then we have a delta connection like this. Okay. Okay, delta connection like this. And then we can take this connection down. Can take this appropriate boxes here. I know we're not getting it properly, but you know what we are trying to do here. Okay, these are the loads, and this is your R, this is your Y, this is your B. And what he is telling, a delta connected balanced resistor load is connected across an unbalanced three-phase supply system. This is an unbalanced three-phase supply system. Sorry, unbalanced three. This is a load, and this is an unbalanced three-phase supply system. Okay. And then, as shown in the figure is given to you with the currents in the lines R and Y specified. Two currents are specified. Determine the symmetrical component. You have to determine the symmetrical component. So this first is this current, and R and Y are specified. Two currents are specified for you. Third, it's not. So first he has given us 20 at an angle of 30 degree amps. Second, he has given us 30 at an angle of minus 65 degree amps. So two currents have been given, and this current has not been given. This current is IB. This is IB, this is IY, this is IR. So IR and IY have been given, 3 has not been given. Now the balance load is balance. This is the solution now. In the balance load, what will happen? The load is given balance. So we know that sum of the currents plus IV, it should be 0. So in this case, 2 of them have been given. So we don't know what's the value of IB. So I can get IB here as minus IR plus IY. Okay, so IB value, after substituting these values, minus what is IR? 20 at an angle of 30 degree plus IY is 30 at an angle of minus 65 degrees. This value, that value will be equal to 34.57 at an angle of 150.90 degree amps. This much of current will be your B current. But so we have IR, IY, all three currents we have now. But what we have to do, we have to obtain the symmetrical components. So you can see symmetrical 0 seconds component will be 0. You calculate that. So IR1 will be 1 by 3. You add them in polar, that summation will come out to be 82.75 at an angle of 38.89, and that value will come out to be 27.58 at an angle of 38.89 amps. And similarly, if you want to obtain negative sequence component, it will be 1 by 3. Summation will come out to be 25.34 at an angle of minus 119.56. So that value is coming out to be 8.41 at an angle of 119.56 amps. So you can find these values. Means that you have to find the third current. The rest of all is very simple. And then we are having another problem in delta connection load supplied from this. B is removed, so I will ask you to do yourself. This is the homework for you. Okay. What else is there? Okay, now very important problem is there. One of these problems, I have taken it from one book. What has been given here, if a three-phase four-wire unbalanced system is unbalanced of a voltage VR plus and VR minus. VR plus and VR minus denote the positive and negative sequence components of drop, that means of voltage drop from R line to neutral. So this will be the VR plus and VR minus will be what? They will be the phase values. So VR, VY, all this will be the phase values. Line to neutral. VL plus and VL minus denote the drop from R line to Y line. So this will be the line values. VRY and YB, RY, YB and BY, these will be the line values. We have to prove this. So let's start the solution of this important numerical. So first of all, you should remember VR, N I am not writing intentionally so that itself means with neutral. VR, VY, VB, these are what? In this case, these are phase voltages. Should be very clear. Number of times I have explained this. Phase voltages. Similarly, line voltages between the two lines, VRY, between R and Y, voltage between Y and B, voltage between B and R, BRs, sorry, RY, YB, BY. No, that is BR, I think. RY, then YB and BR, fine. So this is this is your line voltages between two lines. You know these things. No need to explain. Number of times I've explained it. Now, what we know here, we also know, we know that from the fundamentals, we know VRY is equal to VR minus VY. Similarly, VYB is Vy minus Vb. Similarly, VBR is Vb minus Vr. So these are the values. Okay. These are what? These are positive secants components of positive secants components of line voltage and negative secants components of line voltage. Okay. Components of that we have to see, we have to find it. Okay. And then we have to look into the negative secants components of line voltage. This is our aim, and he has given. So what is VL plus? Let me say that VL plus is a line voltage, and I will take one of the lines. Let me take VL plus. VL plus is clear here. You have to be very clear. VL plus and VL minus don't drop from R to Y. So we have to take it VRY. We have no choice. Don't take it other lines. So we have to take it this line R and Y. He has been given. So this is a positive secants component. So positive secants we already know in how it can be written. It can be written VRY plus, then we have operator A, VYB plus A square operator VBR. This is in standard writing. We have been writing like this, positive secants till now. Zero secants, we don't have any operator A. Positive secants will begin with operator A at second place. Negative secants will begin with A square at second place. So this we know already. So from this, what we can write? So this will be equal to 1 by 3. So I can break down this VRY, VR minus Vy plus A, Vy minus Vb plus A square Vb minus Vr. Moomin, is it clear? Moomin, is it clear till now? Who is there? Sana, roll number 12.
Yes, sir.
Is it clear or not?
Yes, sir.
Okay. Okay, fine. Let's move ahead. So here we have got VRY as VR minus Vy and so on and so forth. Now after that we can write this VRY plus, which is equal to VL plus as. So what we are trying to do now, we'll try to multiply with the operator A. So here we have 1 by 3 VR minus Vy plus AVy plus minus AVB plus A square VB minus A square VR. So this is just we have multiplied by the operator A. Now what we'll try to do, we'll try to, so VRY plus, which is nothing but VL plus, will be equal to, we'll try to combine some terms, VR terms we'll try to combine. So VR plus what? Plus AVY plus A square VB. Okay, this is a positive secants component. This we can write. Then minus we can write here. And similarly, we can write Vy. Okay. We can write Vy plus A. Just a second. Yeah, A VB Yeah, avb, we are writing minus, we are taking common, avb plus a square vr. Let's have a clear va, this va, y, and this we are taking one. Then second we are taking vy, then this avb, and a square, this one vy, yes, a square vr. Okay, fine. So for first one we don't have any problem, we'll keep it like this, keep it in also in the bracket, this one complete. So vr y plus will be vl plus, which will be equal to, let's take them one by one now. 1 by 3 vr plus avy plus a square vb. Okay, we are not writing anything till now. Here we'll write 1 by 3. Okay, we'll write a square vr. I'll write a sequence intentionally for this, plus vy, then plus avb. Okay, now here I will multiply and divide by a. Dividing and multiplying by a for the second term, not for the both the term. Then I have to put complete bracket. So this is for the second term. Now moving ahead, vry plus will be equal to vl plus, which will be further equal to 1 by 3. This we are writing as it is till now, avy plus a square vb. We don't need to do anything to this. Now here I will get 1 by 3 out, 1 by 3a. This is complete bracket here. Then a multiplied by this will be a cube vr. This will be a vy. This will be a square vb. But we know a cube is equal to 1 at an angle of 360 degree, and that is equal to 1. We have seen this. A cube is nothing but 1 at an angle of 360 degree, and that we can write as 1 at an angle of 0 also, because 360 and 0 are the same things. Okay, so vry plus will be equal to vl plus. So this one you can very clearly see this is vr plus. How come? Here you can have a look. vr, vy, vb are phase values. So when they are phase values, so what are the positive sequence for the phase value? vr. This is a positive and negative sequence. vr minus a negative sequence component drop from r to line. So phase values. So here we can clearly see, here we can clearly see vr avy, this is a positive sequence component. So instead of this complete, I will write down what I have to write down. vry plus, I will write down this value. I am going to replace by what I am going to replace this value by vr plus. It should be very clear. This value I am going to replace by vr plus. And again, here, this value, okay, I have to write 1 here, vr plus, it's again the same thing. So let me write, I think I should have written another. Anyway, this is, you can consider it at 1, and this again will be a complete value will be vr plus. Because a cube is 1, there's no problem. Okay. So now we can write here, this is what? This is your vr plus, nothing is in this case. Complete is vr plus divided by 1 minus, this will be 1 by 3a, and this is again your vr plus. I hope this point is well taken, because we know this values here, as himself told, are from line or to neutral. So that's the phase values, and we can simply replace them by vr. This is a positive sequence, positive sequence. So further, vry plus will be equal to vl plus, which will be equal to, we will take out what? We'll try to take out this vr plus out of this. vr plus will be 1 minus, oh sorry, this is not 3, 3 will not come here. Sorry, this is my mistake. Why 3 will not come here? Because that's in the formula. Y3 is not going to come here. This is the formula. 1 by 3 is the formula. 1 by A will remain. 1 by A into VR. Okay, that should be very clear. Okay, so that will be 1 minus VR. Yes, 1 minus 1 by A. 1 minus 1 by A, which can be further written as VR plus A minus 1 divided by A. So therefore, VR y plus, which is equal to VL plus, which is equal to VR plus into A minus 1 divided by A. That's what we have to prove. That's what we have to prove. I will box this result. Can very clearly see this is what we had to prove earlier. Yeah, VR plus is A minus 1 by A VR plus. Now second proof we have to do. Okay. Now second we know, sorry. Okay, second we know VL minus. So what are these? VL minus and VL. These are line values. These are very clearly line values. So VL minus he has written is equal to. So first of all, we have to write VL minus. These are line values. 1 by 3. These are line values. Negative secants component 1 by 3. That will be line values are VRY. So negative secants we have A square first. We know that. VYB plus A VBR. This first point should be very clear. This is a line value, negative secants of a line value. VL minus he has written is VL plus and VL minus are the, so it is for the R line to Y line. So you can also write this equal to, if you want to write down, VRY minus. Just like same we have written VR plus and this one V1 minus. So this is a negative secant, so A square will come first. Formula has to be very clear that you understand already. I have told you. So I can further write it VRY minus will be equal to VL minus will be equal to 1 by 3. I will again break it down. So how will break it down? So I will write this VR minus VY. This is A square Vy minus Vb. This is A into Vb minus Vr. Okay, so this, now what we are going to do, we are going to just multiply it with the bracket. VL minus will be 1 by 3 Vr minus Vy plus A square Vy minus A square Vb plus A Vb minus A Vr. So this is complete. Now again, we'll try to regroup them. One of them we already know. So VL minus can be further written as 1 by 3. So let us regroup first one. Negative secants VR plus A square Vy. We can write it very clearly plus AVB. Have a look. VR A square Vy AVB. So leftover will be, in this case will be minus, or we can write down this complete, then minus 1 by 3. We'll put a bracket for this. Another one also. So leftover is minus is outside A VR again. Yeah, leftover is, yeah, AVR plus Vy, and then what is left? Plus A square Vb. You can clearly see VR plus values will come first. So 3 we have plus, that has gone already. So leftover is A VR negative, second negative is Y, Vy, third negative is this one. So that's left. Now in third, what we are going to do, again in this case, in second case, we are going to multiply by, just a second. So we are going to multiply here in this case by A square by A square. Why A square by A square? Because we want to get this 1. Our aim is to get VR square plus A square Vy. So how we can get this? If we multiply this A square by A, then it will become A cube. Very clearly, it has to be very clear because we have to get the same value here also. What are the value we are getting here? Same value we have to get here. For getting that, we have to manipulate by the multiplying and dividing by the operator. How we'll manipulate that? That value has to be manipulated by multiplying by A square. So we'll get VR. So I'm going to write here VL minus can be further written as, so very clearly this is VR minus. We know this. We have already seen this. So I am writing here VR minus directly now. Minus, now 1 by 3A square will come out. Yes. Then I'll try to simplify it first. How? So that will be AQ VR plus A square VY plus again A4 VB. Okay. So let's simplify it again. VL minus will be equal to, this is VR minus, we have no problem in this case, minus 1 by A square multiplied by 1 by 3. A cube will be 1, so we'll write VR again. So A square Vy, we'll keep it as it is because we have to get the same value here. A4 will be, A4 can be written as A cube into A. So A cube is 1, so we can write it A, that's equal to A. So A4 value can be written equal to A. So we can write it A VB, and it's exactly the same we are getting here. So we can replace this value now. VR minus minus, so this is 1 by A square, we'll keep it like this. So this complete value will become again VR minus. So let us simplify it further. VL minus can be written as VR minus, and this will be 1 divided by 1 by A square, and that further can be written as VR minus A square minus 1 divided by A square. So that value VL minus can be written as VR minus, not minus 1 raised power. Sorry, this is only minus for the notation sake. This is minus. So this is A square minus 1 divided by A square. Okay. So I will box it with the red. That's what we had to prove. And we have proved it. That's what we had to prove here. You can see. Very important question. This is, can be asked, questions like this are asked in the engineering examinations, but this is not in question from the engineering examination. I have not taken from there, but this is, I saw it. It was a very good question, so I thought we need to share it with you. I hope this is clear, and that's all for the sequence components. Now we'll start another topic, secant circuits. Is there any doubt in this case? Yes?
No,
Any
sir.
questions? Huh?
No, sir.
Anybody has a question? Okay, then let's move ahead. The next topic is, this is called secant circuits of a symmetrical transmission line. What's this topic? Secants diagram is above. Figure 1 and figure 2, you can consider it. Secant circuits of a symmetrical transmission line. Okay, this is your figure A. This is your figure A. Okay, let me. This is figure A. This one. and this is your figure B, small loop. Okay, so let's see what we are trying to do in this case. Now, before going, this is a big derivation. Now, we need to complete this derivation. If we can complete it today, okay. If not, then we'll do. This is a big derivation. But before going to this, let me throw some light on what we are doing here. Now, figure 1, actually, I'm talking about the figure 1 first. Okay. Now, before going to that figures, you'll come to know. Now, what we basically have, normally the electrical systems, I have already told you, they will operate in what? In the balance conditions, and they will become unbalanced only upon when the fault will occur in the power system, when the fault will occur in the fast system. So electrical systems operate in a balanced condition, we know that. So I'm not going to write completely, you know this. Normally the electrical systems operate, we know, in balanced conditions. That's why we design the electrical system like that. And they will become unbalanced. When they will become unbalanced, so voltages or currents become unbalanced only when there will be a symmetrical fault. So I'm simply denoting it. When the symmetrical fault will occur, when a symmetrical fault will occur, fault will occur, they will become unbalanced. So normally the systems will operate in a balanced condition and they will become unbalanced only upon the occurrence of a symmetrical fault. This is the first thing. This we already know. I have talked about this number of times. Let us see, let's consider figure 1. Let's talk first about the figure A. That is figure A, this big figure. In this figure, which shows what? It shows section of a three-phase transmission line with a neutral conductor. So what it is showing? Section of a three-phase transmission line with a neutral conductor. We can see that with a neutral conductor. So here you can see three-phase transmission line, phase A, phase B, phase C, and then we have a neutral. So here you have, I'll highlight this, phase A, phase B, phase C, and then we have a neutral. So respective currents are flowing A, B, C, and neutral ion. Voltage is between A and neutral point, and A is VN on the left hand side, one side of the section of this, because we have taken the section, we can't take the complete power system. VBN, then VCN. Similarly on the side, VA dash N dash, VB dash N dash, VDC dash, and similarly from other sides we have taken A dash, B dash, C dash, and N dash, just for the sake of notation. So till now we are writing just now like this. Okay, now points to be noted is, next important points, next is self impedance ZAA is same for each phase conductor. Same for each phase conductor. So you can see self, that means whatever the self impedance of a conductor has to, conductor A is there, conductor B is there, conductor C is there, self impedance of this is same, ZA, B also has ZA, C also has ZA. ZA. Only the neutral will be having ZNN. So that we will mention here. And the neutral conductor and the neutral conductor has self-impedance ZNN. So it's very clear. Till now, we have taken a section of the power system. What is that section? Three-phase transmission line. Three conductors are there and a neutral conductor is there. Second, what we have considered, what we have self-impedance of each conductor. Phase conductor is ZA and neutral will be ZNN. That's all we have considered till now. Next we talk about this point only. We will talk about the currents. When the currents IB, IA, IB, IC in the phase conductors, okay, when the currents they flow IB, IA, IB, IC in the phase conductors are unbalanced, means they are unbalanced. That means then when the fault has occurred, the neutral conductor serves a return path. So it should be very important. So we'll write down this point. When currents IA, IB, and IC in the phase conductors are unbalanced, the neutral conductor serves a return path. Our neutral conductors is the return path. If you do not want to write serve, simple English, neutral conductor will act or will provide you the return path. Roll number 48 is there, Diba? Roll number 48. Okay, 36 is there, Diba? Second Diba.
Yes, sir.
Diva, why I am using the word, I am saying that when the currents IA, IB, IC in the phase conductors are unbalanced, then I am saying that there will flow a current in the neutral path. Have you studied this in the power system 1? It's very clear. When there will be balanced currents in the three
Balanced में zero होता है ना sir?
there will be no current will be flowing to the return path. That's why we
Yes,
take the
sir.
cross section of that we have seen in the power system 1. So here again the question is same. Now once the abnormality will occur and we are considering this and these currents as an unbalanced current, then definitely we will require a neutral conductor so that return current will flow through that neutral current. That will provide a return path. So that's what I am writing this statement. This should be very clear. Now next statement is also very important. Now what's going to happen? Now we have a mutual coupling. You can see here mutual coupling means I have a coupling between this, coupling between this, coupling between this. Mutual coupling. That means between phases there is a mutual coupling. Because of this mutual coupling, what will happen? Current flow in any one of the phases induces voltage in each of the other adjacent phases and in the neutral conductor. See, we have a mutual coupling between these conductors. So what is going to happen because of the mutual coupling, current flow in one of the phase conductors. Say, let's say IA, one of the phase conductors is IA. When the current will flow in the one of the phase conductors, it will induce what? It will induce voltage in each other adjacent conductor. That means when the current is flowing through this, because of the mutual coupling, it will induce the voltage with respect to B, with respect to C, and with respect to neutral. That means it will induce the voltage in each of the adjacent phases and as well as in the neutral. That has to be very clear. Why? The reason is because we are considering the mutual coupling here. Coupling is between conductor A and conductor B, conductor A and conductor C, conductor A and neutral. So we're writing because of this. Otherwise, if we are considering that mutual coupling is zero, so no question, current will flow, but there will be no voltage is induced in the other phases as well as in the neutral. That has to be very clear. Because of mutual coupling, we'll write on this. Current flow in any one of the phases induces voltages in each other in each of the other adjacent phases and in the neutral conductor. So it's to be very clear. Why? Because coupling will exist between various conductors, phase conductors, as well as a neutral conductor and neutral conductor. Okay, that was also important point, so we should know it. The next point is, similarly, it's ion in the neutral conductor induced voltage in other phase. So that has to be very clear, because if we consider ion also, ion is a neutral current. So because of the presence of the mutual coupling, it will induce the current voltage in the other phases also. Ion in the neutral conductor, which will be flowing in the neutral conductor, ion flowing, you can write down like flowing in the neutral conductor induces voltages in each of the phases. So that has to be very clear also, because if we will consider a neutral current, so definitely because of the mutual coupling will be present, so it will induce the voltages in other phases, in each of the phases. That means three phases will be there, A, B, and C. It will induce the voltage there also. Now, next is, let the mutual inductance ZAB. We assume here you can see this is self-inductance. I have told you self-impedance. Sorry, mutual impedance. You can see between A and B, it is ZAB. I have written here. Between A and C, it is again ZAB, and then between neutral, it will be ZA, and we'll see that. So A, B, it's between A and B, it's ZAB. Between A and C, it's ZAB. Between B and C, it is ZAB, and between A and C also it is ZAB. So we'll consider one value. So let the mutual impedance ZAB is assumed between each pair. Each pair means AB, AC, and BC. Three pairs will be there, each pair. Similarly, the mutual impedance between the neutral and each of the phase is taken to be ZN. So also the mutual impedance between the neutral conductor and each phase is taken to be equal to what? Taken to be equal to ZN. So it should be very clear. ZAB is between phase, between each phase. ZAB is between each phase, whether it's a AB, AC, or it's a BC. But when we consider a neutral conductor in any other phase, then it has to be ZAN because the values will be same in all the three phases also. Okay. Now next is a small a bit, then we can stop. If we talk about the voltages induced in phase A, for example, okay, let's say for voltage induced in phase A by the currents by the current that will be flowing in the other two phases and in the neutral conductor will be shown, that will be shown as sources. We will not show them how we can voltage have to be shown as voltage sources. So what I am considering, the voltages which is induced in phase A, for example, by the currents that will be flowing in the other two phases. That means there are B and C phase and the neutral conductor. Neutral conductor is ion current will be flowing in that because mutual coupling is present there. So voltage, just now we talked about that voltage will be induced in the other phases. So those will be how those will be notated as, those will be drawn as a voltage sources, and we will form a loop will be formed in that case, and that is because of the mutual coupling. So we'll consider this in the next class because we are not having enough time to, it's already okay. Sana beta, you can send me the, I will first stop the recording.